Good morning. So client-side data compression. So it looks like compression is trendy now. So we also solving the same problem. So colleagues, we have a problem here. We need to deliver these mattresses to these large transparent boxes through this large tube. So the obvious solution, just make rolls and deliver them. But we also need to remember that we need these mattresses unrolled before we use them. So why this picture here? Because client-side data compression works exactly the same way. So these boxes are storage, these tubes is network, and this mattresses is client page cache. So what is client-side data compression? It's a new last request feature that gives the way of transparently compress and decompress data. It's simple to use. For user, it's nothing, just use. For administrator, it's 2-3 commands to set up parameters. That's it. It already has 4 compression algorithms: LZ4 high capacity, and gzip. But this set can be easily be extended, so any useful compression algorithm can be added there. Also, I think the most important that compression prepared on the client side. So to scale our cluster, we do not need to scale servers. So every client compresses its own data. Also, this solution does not depend on ZFS compression. I know there is a project from Hamburg University. It has quite different ideas. They use ZFS compression. So here it's a different approach. Also, we do not change anything. We do not change LDiskFS structure. And today I want to say that this solution mostly client-side. The next slides will show. So the usage is quite easy. We need to create component and set compression type. So we use LFS set stripe and Z or compress parameter that gets algorithm name and level. So we can choose level. So choose between high CPU load and high compression rate. Also, we can get compression parameters using getStripe. For early adopters, we created a special command that enables this feature. So in first releases, nothing will change it. So for usual users who do not want to use this feature, nothing changes. But if you want to try, you can set up enable compression and set this parameter permanently. Use set param p and play with it. I believe at some point we will enable it forever. I believe. So also some another tools change it to leverage there to work with compressed files. So LFS find has quite a flexible set of parameters to find a lot of types files with given algorithm level, etc. So the idea goes, look, utilities are simple, but how to prepare this? I heard the idea that it's impossible. It's possible, but I need to explain the approach. So, as I said, data user see data uncompressed. So data lay at client page cache uncompressed. So this is this green blocks. But at some point, we flush data and prepare request. At this moment, compression starts. This request compressed to the buffer and then placed to another request. And all required fields are filled. So this is also valid request, but compressed. So we see that this red blocks is compressed data. This gray blocks is free space because compressed data less than uncompressed. And then this compressed data sent to the server. There it laid to the OST object as is. Actually not as is, I will show in next slides. So also to the data compressed based on chunks. So every chunks is compressed separately. And every chunk has its own compression header. So it's basically here it has size and other useful information to decompress it or to find for any useful actions. So important thing here is that every request compressed and decompressed separately. So this approach is scalable to CPU cores. So every request can be compressed on different CPU, more CPUs, more scale. And also scalable to clients. So a lot of clients access to the same file, scalable. So how this algorithm applied? We try always to compress data. So even if some algorithms are not present on the system, it's possible because on the LZO, always on the kernels in the client, and all another algorithms should be delivered by Lustre packages. So we try to apply an algorithm from component. If it's not possible, we try to use the best one, the fast one, LZ4. If it's not possible, we try to apply L0, that always should be, but in case we will write just plain data there. Also, in some case, compressed data arrives, so it's already compressed. Compressed data cannot be compressed. In this case, result size is bigger than original one. In this case, we just place it original data there. So I said that LDiskFS structures have not been changed, but we a little bit optimized LDiskFS code. So it's because the client-side data compression approach uses holes in the files. It always writes at the offsets, at the original chunk offset. And finally, on the LDiskFS side, we have data, whole. So it's and MB allocator optimize this case and resolve these holes for future writing. But these holes will never be written because it's a client-side data approach. So the idea is send special flag to the LDiskFS and write all blocks densely. So no gaps, no holes. Finally, no fragmentation in LDiskFS. So I said that this should be called mostly client-side data compression. So unfortunately, there are some corner cases. So this approach works well in common case that we write data with large blocks that equal to chunk size. In this case, we just get this chunk, compress it, and place. No problem. But in case the data already written, and we want to rewrite it, and we want to rewrite it partly, probably not from start of chunk or not till the end of chunk, or even not from start from page till the end of page. In this case, we need to invent something, and we thought about this, how to do this on client side. It looks too complicated because of distributed last RFS. The client cache is a lot of logs, etc. So it looks like simple idea: just compress and compress mostly, and decompress such a data on the server side, on the OST side, on the OST side. So a little bit improvement here. In case we write an unaligned data, we read whole chunk at the OST size, decompress it, then we modify with data from the client, compress it back and put to the OST. Also, this is actually bottom part, but I mentioned that sometimes we rewrite even unaligned data to the page. In this case happens LL prepare partial page that goes to OST, and partial page came to the client. So we also need to support this to get this request, read this whole chunk, decompress it, and return to the client. So after this, at least this page came aligned, so whole page. We need only add it to our compressed chunk. So also there are some other problems that should be solved. So for example, we use holes, and we can calculate any offset just because we know offset, but we cannot calculate a file size, because after last chunk there is no hole, because this is endless hole. So this is one chunk, and we don't know how this chunk will be decompressed finally. So there is special solution. We need to save object size to the special field. This is look not so difficult, but finally this was important issue, and we will see results in the testing. I will show. We have not fixed it at that moment, this issue, and this had impact in the testing, but finally it fixed it. So also there are some features that it's possible to read raw compressed component for some appliance, something like migration. So there are some cases that we cannot compress its RDMA because CPU has no access to such pages. We just pass compression in this case. Encryption plus compression works now. Thanks, Sebastian. So, but we should always know that compression goes first, because we cannot compress encrypted data. Older clients just see data compressed. So they have no decompression code and see compressed. Also, but the client knows that he can't decompress, so some logic is possible there. So some tests prepared in our laboratory. Client is the most important part here. It's multi-core, more than 200 cores, and a standard exascale appliance. So different sets of input data to see how algorithms work for different types of input. So there are some images, some mixed data, some text like source code and Wikipedia. So, but we assume some results, but finally get some unexpected results, but I will explain why. So, first of all, compression ratio, it's the most important. It's how it finally save it to the disk, how it compressed. So first of all, we see that Linux source should be compressed well, but it haven't. So the explanation is because of issue with file size. So because of this problem, we never compress last chunk, but in Linux source, a lot of small files, and last chunk is the only chunk. So this will be fixed. I hope Linux source should be compressed better. So the same problem probably have sets that have a lot of small files. But for example, the first set shows great compression rates. So also we see that different compression algorithms and levels show different compression rates. So anybody can choose its own level and algorithm for their needs. Also, throughput. We expected that throughput also should be better because compressed data goes through the wire compressor and can be faster. This is part of idea. First of all, it's storage, next wire. But finally we realized that Infinity Band thinks that this holds also data and doesn't pack it anyhow. But this could be solved. We can pack, so holes will be not passed through the wire, and I expect this throughput will be better in future. So also throughput versus CPU, because this client probably it's very important to count client CPU cycles. So how this is graph shows this depends how throughput and CPU has influenced to CPU, but because of Infinity Band issue, probably this is not a good picture, so will be changed soon. And the last one is difficult parameter CPU. They are counted CPU usage, throughput, and compression ratio. And the higher is better here. And we see again that first set shows that at least here compression works well. So it's in this case everything as expected. Also another one shows good results. But we can see this right column that about non-compressed data, and in some cases non-compressed data better than compressed. I think because of the founded issues, they should be of course obviously not better than compressed. Compressed should solve a lot of problems. And finally, results observation. The approach works commonly. For the case that tested, it's buffered, single-threaded I/O, limited performance costing. So it's not so much CPU used, so it's nice. And different input data leverage from different algorithm size and levels. And currently, compression doesn't improve throughput, will be fixed. And I said that there are some issues, will be fixed too. Also, there are some results says that compression chunks are very important. So it is important to choose right chunk size for exact situation. This feature is expected to be available to 2.17. major functionality is ready right now is stabilization, testing. Also, of course, we are going to prepare more testing to see their CPU works, how much works. Also, we need to estimate server-side CPU load in the scaling. Coming soon. So that's it. Thank you. Any questions?
Thank you. We've discussed a lot about this feature already with Artem. I have one more question, since I've seen now that the server is capable of compression mechanisms now, right? Because you've shown that the server, the OSD module, is able to decompress the data when you are doing a sparse write, for example. Why is then the read-modify write still a problem? Because, as you know, it was a really important task for me that the server is always able to decompress the data when you make like a sparse read or read-modify write. Shouldn't it be no problem anymore if the server is able to decompress the chunk?
As I said, the most important advantage of client-side data compression that it's scalable because client spends its CPU to compress and decompress. So compression and decompression of the client sides because we need to process some corner cases. So yes, we can actually in future even make a mode that always be compressed on the server side. But right now I don't see any plans to this idea.
That would be all about reading, because just recently I've made a lot of tests where you read sparse data, as I've shown in this network problem thing. I've made the same for the compression stuff, and for example, you read 1 byte in 1 gigabyte block, and this looping over 1,000 times. If you will need to read the complete chunk all the time, you have like 100 of more data that you have to transfer to the clients. So if you have 1,000 clients and you would read 100 bytes, if you don't decompress them on the server, you will need to read maybe 1 gigabyte instead of 100 bytes. And if the server is able to decompress the chunk and just transfer the only byte that the client has requested, wouldn't this fix the read-modify write problem? Because that was the only reason I started with the ZFS backend, because ZFS is already able to decompress it and just serve the only requested byte, but not the complete compressed block.
So from first glance, this does not solve the problem actually, but probably
yeah,
yes.
Maybe we have to discuss it.
Yeah,
further.
yeah, sure.
On your final performance slide there, you had an interesting ratio. Keep the very final one. That seems to imply that CPU usage, you said higher is better. The implication there is that CPU usage is a good thing.
Thank you very much, Nathan. A special thing that specially was replaced to find this problem. Actually, it was estimated in the right way, but placed it on the slide wrong way. So we should replace them. So less CPU, better, more throughput.
I was curious why you chose it. Okay.
Okay, thank you, Nathan. Sorry, I haven't changed this.
Other questions for Artem? No. Thank you, Artem.